It's time to LeetCode. Lock in.
You heard it. Today we're going to be working on trapping rainwater. This is a hard problem. So let's go ahead and dive into it. We're going to be doing it with Java, as always. So the problem is, given an array of n non-negative integers representing an elevation map, the width of each bar is 1, compute how much water it can trap after raining. So you can see here, first element 0, then you have a 1. This is land. This would be water. 2, land. 1, water. 1, land. And then the water fills up. Um, so you can count 6 units. 1, 2, 3, 4, 5, 6 of rain and return that. And see, check the bounds here. We've got high bounds, 10 to the 4, 10 to the 5. So we'll want to be pretty granular with how we approach this. Um, So the algorithm, this problem, in order to figure out how much rain can be trapped, you need to know the current cell and the neighboring cell's height. Um, so basically, if the, how do I phrase this well? You kind of want to find the height, the maximum height from the left going over on an index. And then you want to find the maximum height from the right going left on that index. And then you want to iterate over the height array and update the answer. So basically, we're trying to figure out looping through, we'll get the left and the right height here. So left being 1, this is water, this is 0, and the one to the right of that is a height of 2. So we know that the water is dictated by the left side here, lesser. Then as you go further, um, you pretty much are calculating the amount of water based off of the maximum and value of the left and right side. So what that tells me is that I need to do a dynamic programming approach instead of, brute forcing and calculating this. So let's dive in here. First off, if the height is 0, then return 0 because we don't have anything to process. Always process your edge cases first. Create our answer variable. This is 0. This is the amount of water. And we'll just get our size. Okay. Size of the array. And now what we're going to do is we're going to be iterating over this input. And we're going to be keeping track of the left max as we go over. And then we're going to iterate over from the right side to the left. Keep track of the right max. Okay. So to do that, we'll create two integer arrays, or int arrays, rather, of the size of height. Of the size of height. And let's go ahead and assign the first value of leftMax 0 equals the height of 0. Okay. And now we want to loop through. For int I equals 1. I is less than size, I plus plus. We are starting at 1 because we want to compare the max of the current with the current's left neighbor. If we started at 0, we would have get a null pointer or index out of bounds because we're trying to check 0 and then 0 minus 1. That doesn't exist. So that's where we're starting at 1. So left max of I equals, we're going to use the math.max always when you get into these situations, the max of height of I or the max of left max I minus 1. Okay. So now we've populated leftMax. Now let's process rightMax. First, we're going to assign it the first value. But since we're going from the right to the left, we're going to be assigning that end value, not the beginning, okay? So rightMax of size minus 1 equals height of size minus 1. And we'll begin processing. Now, since we're doing from the right, you should think the int I would be starting at size minus 2. And I is greater than or equal to 0, I minus minus, because we're iterating from the right to the left. And we're doing a minus 2, same reason we did a minus 1 earlier, because we want to compare the element to the right of it as we iterate to the left. So right max of I equals the max of height of I compared to right max of I plus 1, I plus 1 being the element on the right. Now that we've processed left max and right max arrays, we will calculate the answer by iterating over the height array and updating answer. So answer plus equals, answer is counting the amount of water that we can trap. The math dot min of left max I, right max I, minus the height of I. And now what we're doing here is we're sifting through and we're getting the maxes, and then we're getting the minimum of it subtracted by the height. So that means what we're calculating is the water right here based off the left and right max. Because if the you're calculating right here, you have 1 and you have this max being 2. So the left max of this value would be 1 compared to 2. So you're getting the minimum, which would be 1, and you're getting this water here. So let's return the answer. That would probably help. Okay. And so we beat 64.78% of complexity and memory of 57. And this is done with dynamic programming. So to pretty much go over the high level of what we're doing again, we're looping through, counting the max, the left max at a current interval and the right max at a current interval. And then we're looping through one more time, and we're calculating the amount of water that we can hold based off comparing the minimum of the left max and right max. And then we're subtracting the height of the current element to account for if it's, if it has ground. For instance, right here, you would be calculating 2, but you'd need to subtract 1 for the earth there. You could improve this if you were to update with a 2-pointer approach. This would probably be the most efficient. So we're calculating the left and right max and then looping through again. If you used a left and right pointer, you could calculate this all in one go. And you would be updating as you go. This would lead to time complexity of O of n and a space complexity of O of 1. I hope it was helpful. Feel free to drop in some comments, subscribe, ask some questions. Good luck.